Welcome everybody to the IAPS, to the seminar organized by the IAPS Institute. And this seminar is part of the cycle of seminars dedicated to the missions that get selected for the M7 ESA call. And it's a very great pleasure for us today to have as a speaker today, Federica Marcucci from our institute, that is one of the PI of this mission, in this particular case, the Plasma Observatory, that she's going to talk in today's seminar. Federica is a well-known person here in the institute. She formed in Rome.
I'm enough old.
Well, and I didn't say old. I just said that she's known. She's well known, and she always worked in the field of the study of the physics of plasma, particularly plasma from space. She dedicated a lot of work on magnetic reconnection in plasmas, but also on the data analysis of ion and electromagnetic field in the either from measurement in the magnetosphere from a satellite, either in the solar wind and interaction of the solar wind with the Earth magnetosphere and the influence on the ion sphere. So this is a very interesting topic, and it's linked to the broader topic also of the space weather, from my understanding. Sorry, I work on a different field, but I find it very interesting. And she assumed the later position in the development of the instruments, in different kinds of instruments across the year. In particular, I want to mention that she's the PI of the ionosphere radar that are located in Antarctica at the Concordia station. And also, she is the PI instrument of an interesting mission that is a CubeSat mission, Henon, I think it's called.
Yes, Henon.
Henon.
Yeah,
okay.
It's a name, actually. It's a third name, but okay,
see.
That's another topic.
But to be fair, I found that it's a city in France.
Also,
yeah.
Okay.
Well, anyway, that means it's an acronym for heliospheric and solar.
Heliospheric pioneer?
Pioneer, sorry. Heliospheric pioneer of solar and interplanetary threat defense.
Yes.
So it's a very interesting topic, in my opinion, the interaction and the alert of the information that can influence the sun, the effect from the sun on our system. So this is for your introduction. The floor is yours, Maria Federica. I just invite people that have questions to wait for the end of the seminar, where we will give them the possibility to ask their question.
Okay.
Thank you.
Thanks a lot, Eugenio. Thanks a lot for the invitation. So indeed, I will be presenting you the Plasma Observatory mission. That is a multi-scale mission. I will do it on behalf of a very large team. This proposal and the selection and so on and so forth has been the results of an effort that involved many people abroad, but also in Italy. And we will see a little more about this in the following. So Plasma Observatory, as you can see from the logo, which is an ESA logo, but it's very nice. It's a multi-spacecraft mission, multi-point mission, and in particular is a multi-scale mission, as we will see that we would like to have the possibility to make 3D simultaneous measurements at two special scales for plasmas, that are the ion scales and the fluid scales, and we will see in a moment why this is important. So, we already have problems. Okay, perfect. It's a little bit slow. So this is the outline of my talk. First of all, I would like to show you 3 slides that I think are the core of this presentation and of Plasma Observatory, because I will start from explaining and hopefully convince you that we do need a new multi-scale measurement in the magnetospheric system. Then I will just show a brief slide that summarize the key facts of Plasma Observatory and the status of Plasma Observatory. We will go some detail with the science question of the mission, that are the science requirements. Then we will show a few slides for the mission profile, payload, community involvement, and programmatic framework, and then my conclusion. So why? Every time I make a presentation, I try to present really the very reason why we think we need the plasma observatory, and we think we need plasma observatory now. So all of us knows that plasma observatory is the mainstay of visible cosmic matter. So indeed, we do have to understand plasma physics, which is very complicated, and we have a variety of means of observation. And among these, there are the in situ observation. And what we learned from past mission, but also from simulation that have progressed a lot in the last years, is that it is the coupling of plasma scales, the three typical plasma scales, electron, ion, and fluid, because this drives indeed fundamental properties of astrophysical objects. So from this point, actually, we thought about the proposal of plasma observatory. As I said, plasma is the main state of visible cosmic matter, and we have plasma just outside our lower atmosphere. And indeed, in one of these pictures represent simulation of the magnetosphere, that is in the near Earth space. So magnetosphere is interesting for a number of reasons. Okay, first of all, in the magnetosphere, indeed occurs a lot of fundamental plasma physical processes. These processes are such that with this process is associated energy conversion, particle acceleration, and also sometimes a complete reconfiguration of the magnetosphere that indeed has, as Eugenio pointed out, has effects that are of interest of us, because in some way they affect our day-by-day life. The other things, because the magnetosphere is an interesting place, is that it is very, it is more easiest to put a spacecraft in orbit in the magnetosphere, because it is near us. So magnetospheric system is, as I told you, interesting in many respects. And it is indeed, it has a role for the plasma observatory mission. Just a few more words for the Earth magnetospheric system that I hope will show you why it is so important. So indeed, this is a complex because there are many plasma regions, and it interacts with the solar wind that is impacting on the magnetosphere continuously. It is highly dynamic because we know this also, for example, from the fact that we are able to monitor what is happening outside in the magnetosphere by observation at Earth, because we can measure this effect also by instrumentation on ground. And here we have massive energy transport and particle energization. So the other factor this is important and of relevance for plasma observatory is that these energy transport and particle acceleration are largest when the fluid scales couple with the ion kinetic scales. So indeed, through multi-scale process within non-planar, also these things is important, and non-stationary 3D structure that are governed by wave-particle interaction, these energy transport and particle energization occur and is generated and is mediated. So we do need, because we have to deal with multi-scales, non-stationary and non-planary structure, 3D structure, we do need the new in situ multi-scale, multi-point measurements, because indeed this we do need this to understand how our planet works. That is the famous is a question. So as I said, to understand this process, give a contribution to the space weather compression. And now I think we are at the point that indeed this kind of observation can be useful. We do not want to resolve all the problems, but can be useful for the understanding of distant astrophysical plasma and environments and laboratory plasma. So we do need, as I said, we do need multi-scale measurements. How we can obtain this kind of measurements? We need at least 7 spacecraft. So this is very schematic, but it helps us to understand which is the state of the art and why plasma observatory is necessary. We have had, I think I can use this past for cluster because it's going to re-enter at the end of next year. We had cluster, which was a wonderful mission, and we have MMS. These are multi-point mission with 4 spacecraft. So with this mission, we were able to understand one scale at time what is happening in for the at the 3D having 3D measurement of the structure that characterize and can be found in the plasma environments, but only one scale at time. MMS at some scale, at the ion scale, and for some also, let's say at electron scale, ion scale, according to the separation of the spacecraft, but only one scale at a time, and so cluster. So what we need indeed is to have more than 4 spacecraft. We do need tetrahedra, so 2 tetrahedra of 4 spacecraft, and these can be reached by using 7 spacecraft and having 1 spacecraft that is the common vertex of the 2 tetrahedra. 1 tetrahedra will be at the fluid scale, the inner tetrahedra will be at the ion scale. And with this, we will indeed understand the plasma coupling at these 2 important scales. And of course, this is the next logical step to cluster and MMS. So a few words, the Plasma Observatory science team, it is unveiling plasma energization and energy transport in the near-Earth plasma environment through multi-space observation. This we learned by now. It is clear to everybody here and online. So it is an NISA set candidate mission. We are in the competitive phase A. Final selection will be in June 2026. And the Plasma Observatory indeed targets 2 of the themes that were have been identified during the ESA Voyage 2050 process, and in particular magnetospheric system and plasma cross-scale coupling. There is a large scientific community that is supporting Plasma Observatory from several countries in Europe, and including USA, Japan, and China. The pilot team also is big, as we will learn again later on. I'm the lead proposer, and Alessandro Retino from LPP in France is the co-lead proposer. And yes, he played a fundamental role for many reasons. So we are 2, we are lead and co-lead, and now we are consortium lead and consortium co-lead. So timeline very briefly, just to give you an idea, everything started with the ESA Voyage 2050 process in July 2019. There was the identification of the scientific theme. Then there was the ESA M7 call. Then there was the proposal selection that has been done in 2 steps. Then first a phase 1 proposal was selected, then a second proposal was selected and accepted. Then we arrived at that point, a 5M mission proposal. Then we had a phase 0 with a common design facility study by ESA. And after this study, there was the down selection to competitive phase A of 3M proposal. The future, we will have 2 years or more or less. This is foreseen, but perhaps there will be some. Okay, this is what is foreseen now. We will have the mission consolidation review in May 2025, and mid-April we will have the mission selection review, and with the announcement by the Science Program Committee of which is the M7 mission for ESA, and then there will be a phase B1 for the mission that will be selected in June, and then there will be the SPC adoption of the M7 mission in November. Launch is predicted to be by 2037, a long way to go. So, scientific question with a little bit more of detail. 2 main scientific questions: how are particles energized in near-Earth plasma? Which process dominate energy transport and drive coupling between different regions of magnetospheric system? So for the first one, we have several objectives, and that, as you can notice, these are all dedicated to the understanding of fundamental plasma process. This is how shocks are generated, how are particles energized during magnetic reconnections, energization by waves and turbulent fluctuation. Plasma jets are important, and how all these different processes combine, because often we have a combination of processes that complicate things in a way, but our job is to understand how things work. Here we have a very, just an example, of course, there are many. It is the Bosch-shock. It is an example that shows you why we do need indeed measure at ion and fluid scale. At the Bosch-shock, there are structures that they are called slams that are 3D structures that are not stationary and non-planar, that for sure, as that we learn, play a role in the energization of particles from the thermal to the suprathermal energies. Cluster and MMS both observe this structure at 2 different scales. So we know that there is an evolution from cluster observation at the fluid scales, but we also know that this structure form and depends on the smaller scales, and this has been demonstrated by the MMS spacecraft. So to really understand this process and energization by this structure, we do need both simultaneously observation at the 2 scales. The other question regards indeed all these processes that again a fundamental process operate in the magnetosphere to transport energy and to connect different plasma regions in the magnetosphere. So plasma jets are important. We do have a lot of plasma jets, especially in the magnetotail. How do field-aligned currents, this large system of currents that connect magnetopoles, magnetosphere, ionosphere, are formed and are generated by the fundamental process, which are the key plasma instabilities involved in energy transport, and then, of course, how energy flux is partitioned. Here, again, only one example. It is concentrated in that region, which is called transition region. Okay, it has many names, but let's called transition region. It is where all the phenomena that occur in the magnetotail arriving, okay, not the phenomena, but the plasma jets and the structure that are created in the energetic structure that are created in the magnetotail arrive where the geomagnetic field has resumed as its dipolar form. So there are a lot of fundamental processes because there is an interaction between what happens in the magnetotail and what happens in the near-Earth plasma. And again, here we do need to have multi-point measurements to understand indeed what is happening. Only 1 point or 4 point, it's not sufficient. In this case, we learned again, in this case from the ground-based observation, we know what we can we can observe the footprints of what is happening in the tail, in the farthest region in the magnetosphere. And we do know that a lot of scales are involved. We do need, again, in situ measurements to clarify this process. In situ multi-scale measurements to clarify this process. So we go to the scientific requirements. This should be clear by now. We want to explore with this mission key sense region in the magnetosphere that are the foreshock, that are namely in the foreshock, the shock, the magnetosheath, the magnetopause, the current sheet in the tail, and this transition region that I just about which I just said a few words. The spacecraft, we need 7 measurements points to resolve scale coupling. The spacecraft configuration will be that of 2 tetrahedra sharing 1 corner, and the separation will change along the nominal phase of the mission, because indeed we need a certain number of measurements at the different scales that are different for the different magnetospheric region, for the different magnetospheric plasma population in the magnetosphere. Then what we need indeed, as I said, we need the 7 points of observation. But a very, very important thing that I say now is that at least in 1 point, we need, let's call it advanced measurements. So for studying the context, the fluid scales, we will need observation of particle and field quantity simultaneously at both time fluid scales. But this will serve to provide the context of fluid scales, okay? But to understand, this is a necessary ingredient to understand what our scientific question, our scientific objective. At least in 1 point, we need observation of particle and field quantities that can fully characterize wave-particle interaction, for example. Okay, so we need a payload that is more advanced with what we need at fluid scale, and we will see it in a moment in more detail. So mission profile, orbit and constellation. So the orbit baseline, this has been studied during the proposal and also during the phase 0 study by ESA. His 8 Earth is a highly ecliptic orbit with 8 with a perigee of 8 radii and a apogee of 70 radii and it is a little bit inclined. We have, as I said, 1 mothercraft, and we will see in a few slides how this mothercraft is configured, and 6 small daughtercraft. The constellation will be of 2 tetrahedra sharing 1 corner, again with the mothercraft in the inner tetrahedra, and then we have a nominal duration of 3 years that we need again to have the possibility of make the sufficient number of measurements in each key sense region. These are schematically represented on the upper right figure. And also there is two example of the orbit of Plasma Observatory and the tetrahedra also evolution. This is another point, but I do not have time to talk about it. So spacecraft, these are from PO proposal. So things have evolved because ESA did a phase 0 study, but of course that study is under a non-disclosure agreement, and then there will be the industry studies during this phase 8. So this is just to give you an idea of what we are talking about. So the daughter craft, a small spacecraft, are identical, so no complexity here, are spinning, have a mass that it is around 15 kilos. From the CDF study, we learned that it's more than this, but we will see which will be the output of the industrial studies that are about to start in May. So then we have payload. Again, we are able to measure all the important physical quantities for plasma, electric magnetic field, three-dimensional distribution function of particle distribution. And this will be, for the particle distribution, we will have measurements that are at, let's say, a time resolution that is of the order of the spin resolution, which is 4 seconds at the moment. So this is sufficient for studying fluid scales. On the mothercraft, the payload is more complex, as we will see. So it is a larger spacecraft. It is a slower spinner spacecraft. The payload, again, we will have 3D electric and magnetic field with high sensitivity, because we do need to have accurate measurement and a high time resolution. We will have the three-dimensional distribution function of thermal and suprathermal particles, but on the mothercraft, using more than one unit of the particle instrument, we will be able to go to high time resolution, which are for the ion, for example, of the order of milliseconds. So it is really much more a much higher resolution with respect to the small scale. And we will also have, for example, here it is not written, but the ability of measurement mass composition, that is also very important. So the payload on the mother is more advanced, let's say like that, with respect to the small craft, but on the small craft, we really do not need it, this advanced payload. So this is only a scheme for the payload. Again, I have already described the heat. The only thing I would like to add is that on the mothercraft, we have a field and wave processor and a particle processing unit that will serve as unique interface and processing unit for, on the left, the fields instrument, flux gate, electric field instrument, and search coil magnetometer, and on the right, the particle processing units. It is the interface for the particle instrument. On the daughter craft, the payload is simple. So indeed, we can think of what is on the daughter craft as a unique instrument. They they integrated electronic boards. So it is indeed what this is called, this electromagnetic instrument. We are changing the name actually because there are also the particle instruments that go through this unique interface to the daughter craft, but this is more or less how it is the configuration of the payload in the two kind of spacecraft. So this is more detailed, but I will not go through it because in this, okay, we have indeed which kind of measurement we are going to do, which which details in the type of measurements, energy range, and so on and so forth. But I do not think I have time. If we want, we can go back to these later on if you have question. And this again on the payload, this is the international teams that will provide the payload of Plasma Observatory. So we have contribution from a number of ESA member states, but also key contribution from the US and Japan. So this is the very fast. I will go to this pure scientific organization. So of course, a science studies team has been put in place, and it is assisted and supported by a cross-discipline working group. And these are the composition. Of course, the science study team is the unique interface towards ESA. Serve as the focus of the community, will advise ESA on scientific matters during the phase A study. We do also have a number of thematic working group, because Plasma Observatory is an ambitious mission. I think it's very needed, but it's ambitious. And so we thought that having as much as possible the help of the community is very important. So we have a number of working groups. We have the numerical simulations working group, because indeed we arrived at a point in which the numerical simulation have made a lot of progress. So indeed are a powerful tool, and on the contrary, we miss missions that can test what one can infer using simulation. We do need observation that guide us and help us in the interpretation of and the understanding of the physical process using both simulation and observation. We have multi-point data analysis method, of course. A lot of work was done with the cluster. We have the ambition to do the same for Plasma Observatory. We have ground-based observation, because these are important, are a way to monitor what is happening at large in the magnetosphere. We have a plasma astrophysics working group, because we need that this point has to be further studied, because it is indeed important that we try as much as possible to understand how a measurement can be of help also in these fields, because again, I think we have progressed a lot in simulation and also in observation, also for plasma astrophysics. And then perhaps is the time that we try to put everything together. So we have the scientific synergy, additional science, because Plasma Observatory want to be a mission that include the communities as much as possible. We have a lot of additional science that is important, even if it is not the core of the Plasma Observatory mission. So we have a working group for that. We have public outreach, and then international relationship, because of course, this is also an aspect that is very important. So Italian contribution, very fast. I'm sorry if I forgot some names. I never put names, because I'm usually, I don't know, for how I am, I think it's important, the project and so on and so forth. But at the end, people are what are important as well. The team is important. So I try to put names at the last point. I hope I didn't forget nobody. So the instrument, we have this PI ship of this instrument that is the, okay, I put only the acronym, but it is the ion mass spectrometer. So it is an instrument that combines an optics that select the particle for their E over Q properties. Then we have a TOFS chamber, a time of flight chamber that helps to select, to understand, to add information to understand which is the mass of each particle, and then we have the electronics. So this indeed will be mounted on the mothercraft. This is why there is the M there. We will mount 4 units, so that actually we will have the possibility to measure all the sky, being completely independent from the spin of the spacecraft. And only the electronics of the instrument will be the limitation for the time resolution of the measurements. Yes, there are some information about the resolution in mass, energy range, angular resolution, and temporal resolution, which of course is different from the different ion species. So the Italian contribution here will be that of managing and take care of all the activities of ITIV and calibration. All the elements of the IMS instrument will be provided by a number of contributors. Among the most important one are IRAP lab, NLPP, and then UNH that will provide the University of New Hampshire that will provide the TOF section and the microchannel plate and the steady high voltage power supply. So the other important contribution that we do have, and we have a lot of heritage here. Okay, we have heritage also for IMS because we have been involved in mission like Cluster and also in mission like Baby Colombo, so that we developed the capacity of managing a consortium. This is very important because IMS is a large consortium. Here we have again a PI ship, and this the PI ship of the particle processing unit that will be the only interface between the spacecraft and the particle instrument. So this PPU indeed is central because provides a single power telemetry and control interface to the spacecraft, power switching, commanding, data handling, and a number of data processing that will be done inside the PPU. Here, as I said, we have heritage. We have heritage from Solar Orbiter, and we have heritage for the TOR mission study phase, for which again we have the role of PI ship of the unit that was the interface and digital processing for the particle experiment. Italian contribution is also at numerical simulation used for at this point during this phase A as mission definition, and we have the participation to a number of working groups. The numerical simulation, the multi-point data analysis methods, plasma astrophysics and scientific energy, and this for some of this working group we have the all lead and co-lead. And then again, as Italian contribution, I would like to say that there is a large community that is interested in the science of PO. So we again are trying to be as much as inclusive, and I think that for the scientific objective of Plasma Observatory, the scientific community, international, but also at national level, has a lot of interest because, as I said, Plasma Observatory covers a large number of important scientific themes. So, programmatic framework. This need for multi-scale, multi-points constellation to study space plasma is recognized by a number of agencies. I put here the cosmic vision from ESA, a small piece of text from the cosmic vision paper from ESA, where it was written already a number of years ago that it is now vital to move on from cluster, which has 4 satellites, to simultaneous observation at a much larger number of points. And then again, we have this ESA voyage 2035-2050 study, in which, as I said at the beginning, we have 2 themes that are of interest and that are tackled by Plasma Observatory: the importance of understanding the multi-scale processes and to understand the magnetospheric system that nowadays we know that is more than the sum of its parts. So indeed, this Plasma Observatory mission, I think we could say that is very timely. Programmatic framework of, again, as I said before, multi-spacecraft constellations are in the programs and roadmaps of several international agencies. For example, there is this MAGCON of NASA and NEOSCOP from JAXA, and there is indeed an effort of the international community to try to put together the efforts to arrive to what is called, I still hear the words of Larry Kepko, which is the chair of this Geospace International Scientific Community Group of COSPAR. We want to arrive to a new era of plasma physics. So magnetosphere is a system of systems, and we have that the processes in the magnetosphere goes from very small scales to mesoscales, very large scales, and everything is interconnected. We have a discovery here. We have a discovery here that understand the dynamics. We have an era of in which with satellites we have what is called a quarter system science. Then we have the era of the details with cluster MMS. Now we have to put everything together, and we have to move possibly together. We are as a community are pushing for it to have in the 30s, where a number of missions that have been thought of by the community could be indeed in place, and this would be very nice. This MAGCON, for example, and in this framework, Plasma Observatory would be a key element. So another slide of conclusion. Again, we are convinced that indeed from the 1-point measurements we had a major jump with the cluster MMS to 4-point measurements, and now we need indeed another major jumps going to at least 7-point. And this indeed is, I don't know, I'm in time, I think, is indeed an advertising slides. There are a number of reasons. A lot of them I have already mentioned during my presentation. There are 2 that I think are important. Plasma missions like Plasma Observatory could allow us to form the next generation of European space plasma scientists and engineers after applying multi-point measurement with cluster. We are feeling a lack in here. We are losing competence and know-how. And so in this sense, I think that Plasma Observatory would be important. And then also we leverage European current space as model technology for space application, because indeed this kind of mission is in some way challenging for ESA. And the fact that we are here in the middle, at the beginning of a phase art is, I think, a good sign that this can be improved also in the ESA side. So this is my last slide, and thank you very much for your attention. And that's all.
You, Federica. So thanks for the question. Thank you for the interesting talk and questions.
Thanks to you.
So I see Stefania. Stefania, you can.
So thanks for the interesting seminar and good luck for the research. Now the question was about the redundancy, so to say, what happens if you lose one of the hits.
Okay. Yes, it is easy to answer this question because we were asked this question by the interview, by the panel who made the selection, especially the first one. So they asked indeed what happens if we lose one spacecraft. It happens that we are still able to do transformative science because with 5 or 6 spacecraft, you are still able, in some condition, to retain and to be able to reach all the scientific objective of the mission. We presented for each science, for each sub-science case, what happens if, okay, 7 spacecraft is the full potentiality of the mission. No way this is true. But we presented for each of the science case what happens if we have only 6 spacecraft or only 5 spacecraft. And indeed, with some limitation, but we still indeed can be able to do this, to reach a transformative science, because this we have to prove to ESA, no? That we are able to do transformative science and that the mission is feasible and that it is in the cost cap. These are the 3 main important things that we have to demonstrate. Because, for example, I can mention only this to give an idea. The structure are often 3-dimensional, but sometimes 2-dimensional. So in some case and in some configuration, you can still have the possibility to do measurements, and these measurements are indeed new because you have the possibility to look at what happens at the fluid scale and at the smaller size.
Another question, Anna?
You thought about different primary fields that have different scales. So could you talk a little bit more which are different scales?
Yes, we can go back to one of my slides, perhaps where there is the scales, perhaps somewhere, I put somewhere, I hope. Okay, so 2 tetrahedrals shared in one corner with separation ranging from few tens of kilometers to several thousand kilometers. The main difference, for example, is between the plasma in the geomagnetic tail and the plasma in the dihedral. So there, the ion scale is different, and so we have to go. We had to put the possibility to explore these 2 regions with different separation. The strategy for this is to start with the spacecraft nearby at the nearest distance, and to let them, or not let them, no, it's not wrong, and to increase this distance as the orbit, as during the phases of the orbit. We will not do, for example, like it was given cluster that several times the spacecraft have been thrown together, then they have been put as far apart again, and so on and so forth. Because indeed we do have to be in a cost cap, and having this changing the configuration and the distance cost in terms of operation and of delta V. So the idea, the strategy is indeed to increase the separation distance between the spacecraft during the pre-nominal phase, for smallest distance to the largest distance, and to have the possibility to explore, to have, yes, indeed, the sufficient measurements in each region at the right scales.
That the side is the closer.
Mm.
And different phases
Yeah.
focus on the same kind of.
We will be doing measurements continuously, while the spacecraft will, the distance between the spacecraft will be augmented. In particular, we will have 3 phases, one lasting each 1 year, more or less, and the distance will be increased from the possibility, for example, in the first nominal, in the first phase of the mission, we will study ion kinetic and fluid scale contemporary in the night side. Then we will go to the night side, we will study different scales, and so on and so forth. So we have, let's say, defined for each phase which will be the magnetospheric mission that we are going to study.
Okay. There is a question here.
What do you mean by fluid scale? Is it the scale of
It is the scales where you can describe the plasma without considering that it's composed of protons and electrons. So it is the scale where the MHD works. Yeah, yeah.
Just a question. I mean, the distance is not near the moon, of course. It's much more near the Earth. But is it possible that in the future there always have been some measurements of plasma effects on the moon? It is presumable that for the time you are time scale that you are presenting, there will be something, some problem on the moon. The presence of a further problem on the moon could contribute to your trend.
Every point of observation of plasma properties, it is important at that point. It is the framework that I described. We need to have as much as possible point of observation as possible to understand indeed how our magnetosphere works. So yes, for sure, it is important. We have to aim to this distributed point of observation.
Okay. Also, people from home, if there are any questions, they can write in chat. I can give them the phone. Anyway, I also have, sorry, a curiosity more because I'm not here an expert. How long this kind of mission can last, and if it can overlap with other mission that you said, the cluster that is ongoing.
Okay. Cluster was supposed to okay, I think this is general, but perhaps some of you can help me. Cluster was supposed, the nominal duration was, I think, 2 or 3 years as well. It is the typical duration for a mission. But cluster was launched in 2001 and lasted 20 years, more than 20 years. So the hope is that, of course, we will do the study concentrating these 3 years phase mission, more or less. But indeed, we hope that the mission will last much more than that.
And how important is to have a precise location of the points of the tetra? I think that there is a kind of precision, and then
no. This indeed is important because we have these we have this tetrahedra because we want to compute, for example, currents that are flowing inside these 2 tetrahedra. So how it is important? It is important in the sense the more precise is the knowledge. Okay, they are not controlled. It is the a posteriori on ground knowledge of the position of the spacecraft. The smallest is the error in computing this quantity. So yes, this is part, of course, of the requirements that we have asked for the mission. And indeed, we think that we are able to satisfy it with the means of communication that are foreseen for plasma observatory, because it is not, it is a posteriori knowledge of the position.
So there is a requirement of the
Yes.
how accurate you
Yes.
can measure the.
How accurate is 1 kilometer? Yes.
If there is any other question, I see a question.
Follow-up question about the constellation. So, how will the constellation cooperate together? Do the satellites need to have some precise alignment? We just discussed about the position, and how will the daughter spacecraft transmit the data? So do they need to transmit through the mother spacecraft?
No, sorry, I interrupt you, but no. Okay, this was a study that we considered which is best, an interlink communication between the mother and the spacecraft. But then it was soon realized that we are sufficiently nearby the Earth so that the spacecraft communicates directly with the Earth. The mothercraft and the spacecraft, we communicate directly with Earth. Of course, we will have some means, we do need some means to be able then to analyze data. So for example, we do need some kind of synchronization and sometimes of measuring time on board in such a way that then the measurements are in some way synchronized on the mothercraft, on the spacecraft, on the daughtercraft, and between them, so that we are able not to have not too complex analysis on ground then, because in the beginning, for example, cluster. Let's take an example. The resolution of the plasma measurements and the resolution of the magnetic measurements were different. And the measurements of particle instruments, for example, they started the measure of the distribution function in the middle of the measurement of the magnetic field. There was always a shift between the two. So these kind of things now we can avoid, because we progressed a lot in coordination of things. The name of plasma observatory is not by chance, because we learned that we have we have a number of instruments because the plasma is complex. So no, we do not have a telescope. What I mean, we have 10 instruments that for measuring things, but they have to be used in coordination. These at the time of cluster, for example, was not so clear. TI didn't talk among each other. So in this sense, we did a lot of progress. Not an easy task, no.
Anyway, if there is no other question, I think we can thank the speaker and. Thank you to everybody for attending this seminar.
Thank you very much.